Associate and Partner Webinar Service. Today's webinar topic is Green Laboratories, Untapped Energy Savings Potential. Our speaker today is Allison Paradise. Allison Paradise is the Executive Director of My Green Labs, a California-based nonprofit dedicated to promoting sustainability in laboratories. She has undergraduate and graduate degrees in neuroscience from Brown and Harvard, and after graduating, she spent over 5 years working as a scientific consultant for a life sciences manufacturer. It was from this perspective that she co-founded My Green Lab in 2013. I am Paul Fortunato, the Outreach Coordinator for WCEC and your host of today's show. Webinars are a service provided by WCEC to help inform and guide potential energy efficiency decisions for utility DSM programs and beyond. We at WCEC hope you find these webinars valuable, as they are only offered live to our affiliates and partners who support this research. To help ensure the information in these webinars remains relevant to you, our valued partner, I welcome any and all feedback, including topic recommendations. So please do not hesitate to call or email me with your ideas to enhance the value of these webinars. I will be providing a contact slide at the end of this webinar, so you may quickly get in touch with me or Allison. WCEC's latest newsletter for October has just been released. Our featured content this month focuses on some of the latest behavioral research currently in progress at the center, including a look at how users interact with new, more advanced thermostats and their efficacy for energy savings, and an examination of energy use behavior and interventions for two different ZNE communities, East Sogo in Yokohama, Japan, and West Village in Davis, California. Also included is a new WCEC webinar that you may now view online, and it is on enhancing DSM program portfolios. If you have a question regarding today's presentation, you may ask it directly in the chat panel, or if you would like to speak to the presenter and the audience, you can request to be unmuted from the same chat panel, and I will be monitoring those questions panel and will save the questions and ask them to our presenter in the order they appeared at the end of the presentation. This webinar is officially being recorded, so if you'd like a copy, please contact me directly. I will post our contact information again at the end of this webinar. Today's topic, once again, is Green Laboratories, Untapped Energy Savings Potential. And now, let us welcome Allison Paradise of My Green Lab. Hello, Allison.
Hello. Thanks, Paul. Thanks so much to everyone for joining. So, Paul, I just click next, and it's going to go to my presentation?
I have to open it right now, so here we go.
Okay.
Here you go.
Brilliant. Thank you so much. And again, thanks so much to everyone for joining today. Today we're going to talk about beyond HVAC. Green Laboratories offer an untapped energy savings potential. So I'm hoping that all of you, actually, I was thinking, Paul, if people have questions, I'm happy to answer them as they arise, especially because this topic I'm hoping is going to be new for a lot of you. So if we have things that need clarification as we go along, I think it's probably best to just clarify them along the way. So as Paul mentioned, I am the Executive Director of My Green Lab. We're a California-based nonprofit dedicated to making all laboratories sustainable. That means that we focus on energy, water, and waste. In this particular seminar, we're only going to focus on the energy component of things. So my background is, as Paul mentioned, is as a neuroscientist. I worked in labs for over 15 years. So I'm going to be bringing to you kind of the scientist, neuroscientist perspective on how we can save energy in laboratories. So I think a really good place to get started is to ask the question, well, what is a lab? I really want to make sure that we're all on the same page here. And the definition I decided to use for a laboratory is not the one that I think probably most of you on the phone would be used to using. And that is the one that includes 100% outside air. And the reason I'm not going to use that definition for the rest of today's webinar is simply because I think that excludes some other places that we would consider laboratories. So the working definition we're going to use is that it's a room used for laboratory experimentation, research, or training in research methods, or professional research and observation. So this is going to include spaces that don't necessarily have 100% outside air requirements, but of course we'll include those spaces as well. So now that we know what a laboratory is, we're going to spend the rest of the time kind of looking at three different areas. So first we're going to look at the opportunity. So what is the market opportunity for laboratories in California? We're then going to go through some specific case studies of laboratory equipment and ways that we can save energy by either modifying the equipment or looking at kind of new technology. And then finally we're going to conclude by looking at a proposed model for addressing some of the challenges around energy efficiency in laboratories. That's kind of our roadmap for today. Now that we know what a laboratory is, let's look at what we know about the market space in California. Sorry, I keep hitting page down instead of next. Okay, so we know that laboratories are the largest consumers of energy at research universities. This is something that's been well documented. Any of you who work in the academic center probably know that research labs are 30% of all the building space on campus. So they're huge energy consumers. We also know that in California, we have the most research universities in the country, which is great, but it also means that we're using a lot of energy. And we know that in California, we have the highest density of biotech and pharmaceutical companies, even higher than in Massachusetts. So if we just think about academic and biotech and pharmaceutical laboratories, you can see that already in California there's a huge opportunity. This is, of course, excluding other laboratories, such as those found in hospitals, forensics, any local laboratories that might do water testing or any other sort of testing on the local level. Any of our industrial laboratories, all of those clean rooms, for example, in Silicon Valley are excluded in this analysis. So you can see that really the opportunity is quite large in California, which is exciting. So why are laboratories so energy intensive? So if we take aside for a moment the 100% outside air requirement and just look at our general definition, one thing that's common across all laboratories is they all use energy intensive equipment that's generally on 24/7. So that's one of the key reasons why these labs use so much energy. So I hope that you can see we've kind of built a case that California has a lot of laboratories and they use an awful lot of energy. So if we look at our existing lab space, this is kind of an empty lab shown here for those of you who are looking at the webinar right now. You can see our fume hood. I don't know if you can see my cursor or not, but I'm pointing to the fume hood in the center. This is typically what people address when they address laboratories, right? The space and sometimes the fume hoods. But what we're going to focus on today are the things that are plugged into the wall. Oh, I guess the animation doesn't work on this. That's okay. Things that are plugged into the wall. So there's going to be a lot of things on this screen, and I apologize for this. I had it kind of going in order so that we could talk about each one. But on the screen here, you'll see things ranging from small appliances, such as heating blocks, shown at the bottom left-hand corner in case you can't see my cursor, up to the thing on the bottom right-hand corner, which is a mass spec machine that is usually on 24/7, requires 4 vacuum pumps to be on at all times, to ultra-low temperature freezers, shown here kind of at the bottom center, to microscopes, just to the left of that, incubators all the way at the top left corner, lasers, shown at the top right corners, and a couple of other pieces of equipment. So we have a lot of different types of equipment that can be plugged into the walls in laboratory. That's really the take-home message of this slide. And a lot of these pieces of equipment might not be things that you've considered before. I think the conversation has usually tended to focus around fume hoods, and sometimes it's extended to ultra-low temperature freezers, but you don't often hear the conversation extended to lasers, for example, or these mass spec devices or microscopes or incubators or things like that. Okay, so we know we have a lot of things plugged into the wall, but it turns out very little is known or communicated about the energy consumption of laboratory equipment. And I want to really take some time to address this and to understand why that is the case. So if we look at this schematic here, we can see if we start on the left-hand side with architects, typically a building starts to be constructed, it's going to be constructed, or we're going to do some sort of retrofit of a building, we consult with the architects. And the architects are in communication, constant communication with the facilities managers, right? That's what this arrow represents here. And the facility managers are in constant communication with the energy managers, who are also in communication with the architects. So we have this nice little circle here on the side that represents how a building gets built. The problem with this is the scientists over here on the right are usually completely left out of this. So these people, the facilities managers, the energy managers, the architects, they design this really wonderful building. And then you put the scientists in, and all of a sudden things don't work the way they thought they would. And we've seen this kind of over and over again. There's a really beautiful net zero energy building in San Diego, the JCVI, the John Craig Venter Institute, that was beautifully designed. And it was net zero before all the occupants and all the equipment was put in. And that's simply because people just don't design with input from the scientists. And if we look at this kind of on a more equipment-based level, you can see that the disconnect gets to be even larger. So if we kind of look at it now in terms of what the function of these people really is, when we look at equipment and once the building is operational. What we see is that the people who pay the utility bills, right, are not the people who purchase the equipment. And that disconnect really has led to this lack of understanding of how much energy laboratory equipment really uses. In addition, you can see that the people who sell laboratory equipment to the scientists, they exist over here on the right in essentially their own bubble. So they communicate with each other all the time. So people who purchase equipment make recommendations to the vendors update their equipment accordingly, and so on and so forth. But these people never speak to the people who are paying the utility bills or have any concern about energy. And as a result, vendors aren't necessarily motivated at this point in time to do much to make their equipment more energy efficient or to even understand the energy consumption of their equipment. So oftentimes what they'll give you in the manual is sort of the least amount of energy requirements for that piece of equipment based on some sort of spec that might have been spec'd out many years ago. So there's really not a lot of emphasis on that in terms from the manufacturer's perspective. So this is what we're dealing with right now. And for those of you who might have been in this industry for a while, I suspect this might start to look a little bit to you familiar in terms of data centers. So this is where data centers were maybe 10 years ago, where you had the people who were paying the utility bills and the people who purchased all the servers not speaking to each other at all. And as a result, you had data centers that were consuming more and more and more energy. But we've seen now over the past 10 years that trend has really reversed, and now there's a lot of emphasis on energy efficiency, and what we're hoping is that model will then be able to be implemented in laboratories. So before I move to the next section, are there any questions? Okay. So the opportunity for energy reduction in laboratories can really be broken into operations and design, and today we're going to really just focus on operations. So we've got facility and equipment operations. Those are short-term, driven by technology and behavior. And then we have design, which would then come later, right, because that's being driven by operations. So the first part of this is to look at operations. And we've spoken a bit about facility operations, and I think most of you on the call are probably familiar with what the opportunities are in facilities. So those include, of course, ventilation rates, heating and cooling, lighting, water systems, compressed air, gas systems, things like this, large systems. But the rest of the presentation is going to focus on the equipment operations. And this is just a very short list of some common equipment that's found in laboratories. This is, represents maybe 10% or less of the equipment that could be found in laboratories, but just some common pieces that I pulled out for today. I wanted to pull this up and show you, for those of you who are looking at the screen, to be able to see a study that was done in an actual laboratory space in the UK. So from that list of equipment that I just showed you on the previous slide, several of them are listed here on the left-hand side. So you can see incubators, the freezers that we talked about, ice makers, the PCR machines. All of these are listed here on the left. And then they have approximated how much energy these things consume because, again, not a lot of information is known about that, as well as their typical usage per year, multiplied by the number of different types of equipment found in the laboratory, and you can see what the estimated total energy consumption is per year. And the reason I wanted to show you this is just to demonstrate how this is one building in one academic institution in the UK, and they have 57 minus 20 freezers, which represent about 250,000 kilowatt hours per year of energy consumption, just from that alone. If we look down here, water baths, which might not have been something on your radar before, they have 31 of them, and those use about 100,000 kilowatt hours a year, just in that one building alone. So I hope you can see that there's really some opportunity here based on what we know about typical energy consumption and typical hours of usage multiplied by the numbers of these types of equipment. We're going to focus on 4 specific types of equipment in laboratories. We're going to start with fume hoods because I'm hoping that most people are familiar with them, but just to make sure that everybody is on the same page. And then we're going to speak about ultra-low temperature freezers, autoclaves, and then one that I'm hoping is new to everybody on the call, microscope lighting. And the reason we're focusing on just 4 is that, well, of course, the list in the previous slide is quite exhaustive, and I don't want to keep you here all day to go through every single one of these. But also, I think each one represents a unique opportunity and kind of can stand in for what I would call be a class of different types of equipment. So let's start here with fume hoods. So we've estimated that there are a minimum of 85,000 fume hoods in California, and this is based on data that was collected by Lawrence Berkeley National Labs. It's probably quite a bit higher. Almost all of the numbers that you're going to see in this presentation are based on numbers that we ourselves could verify by talking to people. As a result, they're probably underestimated quite significantly, but we think the point is made nevertheless. So we've got 85 per year per fume hood, which means that we're using about 3.4 billion kilowatt hours a year. There's something we can do about this, and I hope most of you are familiar with this. So these would be what are called constant air volume fume hoods, but we can retrofit them or install new ones that are called variable air volume fume hoods that have occupancy sensors that will automatically close the sash when people are not working in the fume hood. If we install these instead, what we see is that we can save about 25% energy. So if we just installed 50% of the fume hoods in California with VAV and occupancy sensors, we would save about 850 million kilowatt hours a year, which I think is quite significant. In addition, there are kind of ancillary benefits with making some of these changes in laboratories. And in the case of fume hoods, one of those benefits is improved safety. And this is really important to recognize the additional benefits, especially when you're thinking about how you would want to engage occupants to be able to make these changes. So as we talked about in that slide several slides ago, that the people who pay the utility bills are not the people who are purchasing the equipment. Because of that disconnect, you want to make sure that when you're trying to engage scientists that there's some benefit that they can see for themselves aside from the energy savings. And in each one of these cases, you're going to see that there's some benefit to the scientist. In this particular case, it's improved safety, because when the fume hood sash is shut, there's less chance of people being injured by a potential explosion in the fume hood. Okay, so now let's move on to ultra-low temperature freezers. So we estimate, based on surveying 20 institutions in California, that there are at least 15,000 freezers, ultra-low temperature freezers. So these are the -80s in the state. Again, this is based on just 20 institutions, so you can bet this number is going to be quite a bit higher than what we've estimated. We know that they use around a minimum of 7,300 kilowatt hours per year, and these numbers are based on field studies as well as the studies that were done in the UK. So we have kind of a baseline for kind of the minimum energy usage, which means that in total in California, we're looking at least 110 million kilowatt hours per year for ultra-low temperature freezers. And there's a picture of one in the corner here in case you're not familiar with what they look like. That's quite substantial, a real substantial opportunity. These guys are, of course, running 24/7. So if we could do something to reduce the energy consumption of these, it would really have a significant impact. It turns out that there is a new model of freezer that is thought to use quite a bit less energy than the standard ultra-low temperature freezers. This model is called a Stirling freezer. So click over to the next slide. The Stirling freezer uses a different type of, kind of a completely different model or system in order to make the freezer work. So a standard ultra-low temperature freezer works very much like your freezer at home, or your refrigerator at home. It is a compressor system. So the ULTs use a dual compressor system, and that's why they tend to use so much energy. Stirling freezers don't use that at all. They use what's called a Stirling engine. And as a result, they have a lot fewer mechanical parts. They tend to break a lot less. And because they're not using a compressor, they use about 55% less energy. So if we switched all of the freezers that we know about in California to Stirlings, we could save 55% energy, or about 60 million kilowatt hours a year across the state. Additional benefits, well, of course, we all know, I said this was beyond HVAC, but we all know that there's going to be HVAC-related benefits to switching out something, for example, from a standard ultra-low temperature to a Stirling, something that's using less energy, that's kind of radiating less heat, is obviously going to have less of an impact on the HVAC system. So by switching to a Stirling freezer, you're also going to have this ancillary benefit of not having as great of an effect on the HVAC system. And if any of you have ever been in a room where there's a lot of ultra-low temperature freezers, I can assure you that this is not only going to make people on the facility side happy, but also scientists who are working in the space, because those rooms tend to be extraordinarily warm and very uncomfortable places to be in. In addition, for the scientists specifically, because the Stirling freezers are using a completely different technology, they tend to last a lot longer. So those compressors often fail, and this can lead to loss of research, loss of valuable samples that are being stored in these freezers. So if you have a freezer that's more reliable, that's of interest to scientists. Are there any questions about those two so far? I hope it's pretty straightforward, but if there are, just let me know. Okay. Let's move on to autoclaves. So autoclaves, for those of you who aren't familiar with these, are really large sterilizers. So they're used to sterilize laboratory equipment or hazardous waste coming from laboratories. A picture of one is shown in the bottom right-hand corner. They're quite large. I think without the scale, it's kind of hard to tell, but I would say most of them stand at least as tall as a person and are at least as wide as your arm span. So they're quite large. At the University of Liverpool, they did a study on how much energy was being used by their autoclaves, and they found that just to generate the autoclave steam you can see in the building represented 20% of their energy use. So this was third to ventilation-related energy equipment, and then autoclave steam. So you can see that these are obviously using quite a bit of energy. It's really unknown how many of these there are across the state. And because of that, I'm not going to even hazard a guess, but I will just look at a case of a single autoclave. If we look at a single autoclave, and actually just to back up, I'm not going to guess how many there are, but to give you an idea of how many there might be, it's not uncommon to have at least one or two of these per floor in a laboratory building. So if you just think about all the laboratory buildings in your territory or where you're located, you can think of there's at least one or two of these per floor. And each one of them is using about 92,000 kilowatt hours per year for a single autoclave. And the autoclaves that tend to be installed in laboratories are called medical grade autoclaves, and the reason they have that name is that these were the autoclaves that are commonly installed in hospitals as well. So they're used to sterilize hospital equipment. So that's why they're so big. In laboratories, it turns out that's not really necessary. But again, because of this disconnect between the people who are designing the space and the people who are occupying it, you end up with a lot of these medical grade autoclaves in laboratories anyway. If we were to instead not use medical grade autoclaves, but instead use something called a research grade autoclave, these use about 11,000 kilowatt hours per year, or representing almost 90% energy reduction, just by switching from something that's a more appropriate size for the work that's being done in the environment. And again, this is really looking at specifically kind of plug load and steam generation, not looking at any of the effects that it might have on HVAC, which is listed under the additional benefits. One of the other really cool benefits of switching from something like a medical grade to a research grade is that in the medical grade autoclave rooms, they tend to have their own rooms. It's not uncommon for those rooms to have themselves 20 air changes per hour. And that's because it's assumed that these are running all the time. They get very, very warm, and they are often used to sterilize things that might have an odor to them. By switching to something that's a bit smaller, a bit more compact, that we know isn't being run all the time, we can reduce and dial back the number of air changes per hour. So research-grade autoclaves are really only run about 5 times a day at most. There's a really interesting study that was done at Stanford where they had a room with a medical-grade autoclave, and then they had a switch so that researchers could actually increase the number of air changes per hour when people were actually running the autoclave. And I think that's another kind of benefit that we can see around autoclaves and really fine-tuning the spaces in which they reside in order to help reduce some energy consumption. In addition, I mentioned steam, and these are sterilizers, so you might be thinking, of course, water. And being that we're in a drought, I think it's worth mentioning that medical-grade autoclaves are using about 50 gallons per cycle with an additional 20 gallons per hour to cool the steam generator, whereas water-efficient research-grade autoclaves use about 20 gallons per cycle. So we're saving a minimum of about 40 gallons per cycle, or about 66% water, just by switching to something that's the appropriate size for the task at hand. So I hope that you can see in the last three examples that there really are some opportunities, and that those opportunities actually look like they might have some solutions. So it's not just that we have a lot of equipment and there's nothing we can do about it, but we have a lot of equipment and there are things that we can do about it. We just currently really aren't doing those. And again, this I'm hoping is new for pretty much everybody on the line. So fluorescence microscopes are used to look at samples that have been labeled with something that's fluorescent in research labs across the state and across the world. I have the arrow here pointing to the light source for this microscope. So this has a mercury bulb in it, or a metal halide bulb, that's used to generate the spectrum of light that people use to look at their samples. So the minimum in California, again, this minimum number is coming from manufacturers who were willing to share their sales information with me, so it's definitely a minimum. It's about 4,000 in the state. And each one of these lamp houses uses about 2,500 kilowatt hours per year per microscope, which means that across the state we're using about a minimum of 10 million kilowatt hours per year just in lighting our microscopes. And the reason I like this example is it's much smaller than the other ones that I've shared with you before, right? The freezers, 7,300 kilowatt hours a year. The autoclaves, 92,000 kilowatt hours a year for each one. But in spite of the fact that each one of these uses a lot less, cumulatively it's still quite a bit. And there's something we can do about it. So I'm sure for all of you who are in lighting and can guess where I'm going with this, right? So if we switch from metal halide bulbs to LEDs, we can save at least 60%, or about 6 million kilowatt hours a year. In addition, there's something really cool that happens with the LEDs, which is that you can turn them off. And mercury and metal halide bulbs are things that people tend not to turn off because they have a really long warm-up time of about 30 minutes. So people just leave them on all day because they never know if they might need them. As a result, you've got equipment that's running all the time during peak hours when people usually aren't even using it. If we switch them out to LEDs, not only would we reduce the amount of energy being consumed at the plug, but also the amount of energy being consumed during peak hours, which is important. Additional benefits for this are a little bit more widespread than the ones that we've talked about before, and that's simply because this piece of equipment tends to be something that is actively being used in research as opposed to the other pieces of equipment that we've talked about, which are, I would say, more sort of things that people don't pay as much attention to. I guess some labs are not. They're more storage sites or things that allow you to get to the next experiment, whereas microscopes are really an integral part of the experiment. So additional benefits include improved safety and performance. So the LEDs actually perform better than the metal halides for almost all experiments, and they're safer for you. They're not under high pressure like the metal halide are, so they're not prone to explosion. There's reduced maintenance costs because the LEDs last, of course, quite a bit longer than the metal halide bulbs last. And the LEDs do not contain mercury like the metal halide or the mercury bulbs do. And, of course, reducing mercury consumption in general is always a good thing, especially in hospital labs. Okay, so we've gone through just 4 of the list, which was a small list compared to all of the things that are in laboratories. So I hope that you can see that there's really a lot here that we can do in labs. Not all of the things on this list have something that is more energy efficient that could replace it, but I think it's the case that there could be something more energy efficient that could replace it, or that people could make their equipment more energy efficient if the market were driving it in that direction. So we've spent a lot of time talking about equipment replacement, and I just want us to kind of focus again on those 4 main areas and talk about some other things that have nothing to do with replacing equipment, and that is around behavior. And the reason I want to mention this is because, of course, behavior is a critical component to reducing energy consumption in laboratories, and it's something our organization works with a lot. So I wanted to just share with you some of the behavioral components that can be changed around these different pieces of equipment. So I think for those of you who are familiar with fume hoods, we are all familiar with the Shut the Sash campaign, which encourages scientists to close their fume hood sash in order to save energy and then, of course, for improved safety. I wanted to share with you the sticker that we came up with for the fume hoods. I know that there are a lot of them, but I quite like this, so I wanted to share it with everybody. This is a clear sticker. It goes on the inside of or on the glass part of the sash, so it's something that's really visible to the scientists. It's also fun, so it makes people smile, which is always a good thing. People kind of are sick of regulations and being told what to do, so it's nice to have something that's a little bit fun. And you might notice that on his lab coat of the scientist, it says, "Be good in the hood." And that's our slogan for people. So we're telling people to shut the sash, but be good in the hood is really the campaign. And the hood, of course, meaning the fume hood, but then we're also taking this character and kind of making him be good in the hood as in the neighborhood of your laboratory character for all these other types of behavioral changes that we want people to do in the lab. So the campaign is called Be Good in the Hood, and we just happen to start with fume hoods and the Shut the Sash campaign. So this has been rolled out in several places, several universities across the state. If we look at ultra-low temperature freezers, there are some behavioral things that people can do to help reduce energy consumption of these as well, aside from just purchasing a new one. Temperature tuning is one of them, as well as proper maintenance. So by temperature tuning, we mean changing the temperature of the freezer itself. When I first started working in laboratories, these freezers were known as -70s, not -80s. And the reason they started to be set to -80 was actually had more to do with marketing than the science. So if you talk to people who are product managers of these freezers, what they'll tell you is that at some point it became challenging for them to differentiate themselves in the marketplace. So they started just going lower because that was the easiest way for them to get recognition. And now it's not uncommon to see these set to -86, which is, there's really no biological reason for a freezer to need to be set to -86. In fact, that temperature is quite close to the temperature you might want to store things at in liquid nitrogen. So it's really just kind of a race to the bottom for no reason. So we try to educate people on that, as well as proper maintenance. So cleaning the coils, defrosting the freezer every once in a while can really lead to energy savings. If you chill up your freezer from -80 to, say, -70, where they used to be set, you can save 20 to 25% of the energy. So it's not unsubstantial. And the same thing with maintenance. I mean, cleaning the coils, getting rid of the ice can also save a pretty significant amount of energy and prolong the lifetime of the freezer, which of course makes scientists happy. So we've come up with a campaign around this, of course, called -70 is the new -80. This is a magnet, a picture of a magnet that we've been putting on freezers across the state to encourage people to chill up the temperature of their freezer. Just a really simple thing that they can do to save energy in the lab. And of course, because the compressor isn't working as hard to keep the temperature at -80, it means that the freezer has a chance of lasting a bit longer. Additional energy efficiency opportunities around behavior include, for autoclaves, consolidating loads. It's not uncommon for people to run one thing in an autoclave. In fact, I used to do it all the time. And I'm embarrassed to say that because I just never thought about how much energy or water it was using. I just thought, oh my gosh, I need my pipette tips to be sterile for an experiment in an hour. So I'm going to run this thing that just so it's about a half an hour. So it's using about 40,000 kilowatts. And all the water that goes with it, 50, 70 gallons worth of water for one thing. So we've been encouraging people to consolidate loads with neighboring labs or just wait and do their sterilization maybe twice a day in order to save some energy with autoclaves. And people are actually pretty receptive to this once they learn how much energy these things are really using and how much water. Again, people are very sensitive to the drought. And finally, around microscope lighting, some of the behavioral things that can be done is just to simply turn it off. So as I mentioned, people tend to just leave these on all day, whether they're using them or not. And getting into the habit of turning off equipment that you're not using is a really good way of reducing energy in the lab. And this goes for not just microscope lighting, of course, but for any piece of equipment that's left on all the time. So heating blocks are a really good example of that. A water bath, another great example. People will leave these set to, I think the heating block in our lab was often set to 65 degrees Celsius. It's quite warm all the time. The heating bath also set to 37 degrees Celsius all the time. And then, of course, because it's warm all the time and the water bath requires water, you have to keep filling it up with water, otherwise it dries out. So it's another waste of water associated with that. Okay, so we've talked about all the different types of equipment and possible replacements for types of equipment in labs. Not all, but 4 different cases, I guess, and 4 different types of replacements, as well as behavioral changes that can be made in laboratories. So let's tie this all together into something, kind of a comprehensive model of what it is we really want to do in laboratories to help address energy consumption. So the model that we've proposed is called a Center for Energy Efficient Laboratories, or the CEEL. The functions of the CEEL are shown here after the arrows. So one of them would be industry stakeholder engagement and outreach. Another would be training. I'm going to skip the middle one for a second and go to audits, and then, of course, market research. And market research is the obvious place for us to start because, as I've been mentioning throughout this presentation, there really isn't a lot known. I mean, we've been guessing at the numbers. We've been guessing at how many. We've been sort of guessing at the energy consumption. So for us to really get a handle on what the market looks like, I think it's a good first step. And then from there, we're probably going to go to the middle, which is third-party equipment testing and certification. And the reason for that, of course, is now once we know what the market looks like, it would be really helpful for us to actually have some idea of how much energy these pieces of equipment are consuming and really understand, well, where's the benchmark, where should that be? And from that, create deemed rebates and customized incentive support so that we can incentivize the people who are purchasing the equipment to purchase the more energy efficient models. So we can bypass this problem of the people who pay the utility bills not being the people who purchase the equipment. So we're really excited about this model. This is something we've started. PG&E is already supporting us for the market research component, as will, I think, SCE and SDG&E will also be supporting us for this as well. And this is something we plan to conduct actually starting next month. So hopefully the next time we convene, we'll have some really interesting data around what the real opportunity is in the state. So I've mentioned we a lot, but I'm the only one talking, so I think it's important to understand who this we is when it comes to the Center for Energy Efficient Laboratories. So our core team includes, of course, our organization, My Green Lab, as well as KW Engineering, so they're going to be responsible for doing a lot of the consulting work, the training, the work paper measures. Of course, our partner, the WCEC, who will be helping us do the third-party equipment testing, the outreach, and the training, and Fisher-Nickel, or the Food Service Technology Center, who will also be helping with third-party equipment testing. And if you're familiar at all with the food service industry, this model might look familiar to you because we basically took the model for the food service industry and kind of said, well, this looks really similar to laboratories, actually. A lot of the same challenges exist. There isn't a lot of data. There aren't a lot of protocols for what it would even mean to test equipment for laboratories. So because of that, we thought it would be great to partner with Fisher-Nickel and the WCEC and really figure all of that out. So that's the plan moving forward around laboratory equipment and energy efficiency in laboratories. And I hope that it's hard not being able to hear a reaction, but I hope you're as excited about it as we all are. And in conclusion, I hope you can see that laboratories represent an untapped energy savings potential. And I hope that you're able to see laboratories maybe in a different light, in a different way than you have before. My contact information is here at the bottom of the slide. Please feel free to email or call anytime if you have any questions. And I'd love to hear your thoughts and any questions you might have about the information that was presented. So please feel free to ask.
Thanks, Allison. That was great. It's interesting because we at the WCEC, we are actually going through exactly the issue that you were talking about earlier, where you have the builders and the architects and designers who have designed a space. We're in West Village, and so this area is supposedly the largest zero net energy community. Unfortunately, they were not necessarily made aware of how much energy we would use in our laboratory as well. So there's that disconnect that you talked about earlier. Also, what you're talking about the lack of incentive for the person occupying the space and using the energy to deal with energy because they're not paying the energy bill. We're actually extensively studying, at least in a behavioral sense, that issue at West Village as well, because the apartments here, the students, the residents here, they pay a very large. It's an expensive place to live, and so they pay that. They don't have to pay an electricity bill, and they assume, since there's all this solar that they see on all these roofs, that they could basically use whatever they want. And obviously that's not the case, because the zero net energy is modeled based on a specific amount of usage, and obviously gone well beyond that. So at least for me, and the way that we've been seeing this, is that disconnect between who pays the bills and who uses the stuff is a very large one. What types of mostly market research at this point? And I know that's actually the first phase, and that makes sense. But do you have an idea, if you could see into the future, the types of incentives that you would try to promote, or at least work with utilities to promote, to basically motivate the energy users to make energy conscious decisions?
Sure. I mean, actually, I think it's pretty simple. It's not very complicated. Most people in the scientific community are pretty much motivated entirely by money. So, they don't have a lot of money, right? Their grants are really tight. So any amount of rebate that you could offer them to at least make the more energy efficient model be comparably priced to another model, I think that would be enough to tip the scales. It's really just the case that they're not considering it, and they tend to be more expensive. So it's not worth that extra added amount. But what we've seen, at least around freezers, is that universities that offer rebate incentives for people, so specifically through the university, that's what they've been doing, is offering these rebates to incentivize people to buy Stirling freezers instead, and they've had a lot of success with that. So I think we kind of see that that's really what motivates scientists. It's going to be saving money one way or the other, So
I'd like to, open it up again to anyone if they have any questions. That was a very thorough webinar, so maybe there aren't as many questions. So I'll leave it open for a few minutes and see if you guys have anything to say to Allison. Allison, I have one more question for you. Are you in also direct connection with the manufacturers? Have you gotten kind of their seal of approval, in a sense, where you're talking to them and saying, hey, we need to third-party test your stuff, because even though I'm running numbers here and telling people that this is approximately what we're going to be saving, we need third-party verification for this, right? So that's you know what I mean? Because we, at WCEC, we do a lot of testing for evaporative products, and when we get when the utilities get presented by the manufacturers the savings or deemed savings that you may get from their products, it's not always true, as to how much savings there really is. So we are kind of the third-party objective testers. Like, you had already put up that you would add, Mr. Nickel on that list for third-party testing. But have you, had that dialogue with manufacturers to get at least some of that started, where if they're so confident in their numbers, why don't you send it to the WCC or to Mr. Nickel? Let's put a stamp on that.
Yeah, absolutely. Can you hear me? Because you got a little garbled on my phone. Can you hear me?
Yeah. It's garbled, but that's the internet. But do you hear what I said?
I heard you. Yeah, you sound a bit like you're talking to the telephone. But I heard you. as long as you can hear me, then that's good. I think we did engage a lot of manufacturers, and that's a great question. Their support is critical to the success of the center, right? So we had originally proposed actually not only market assessment, but also doing concurrently doing some of the testing, which the utilities said was not a great plan, so they kind of wanted to see the market first. But because the original plan had been to do kind of concurrent market testing, we reached out to freezer manufacturers and autoclave manufacturers and got their buy-in. Freezer manufacturers are actually really excited about this. They had been working with the EPA for a while to try to create standards for energy consumption, and that fell through. I think that was a 6 or 7 year process, and it just is bogged down by, I think, a lot of bureaucracy. And one of the things that we have that's really great is that we don't have a lot of bureaucracy, and we're really motivated to move forward, and so they got really excited about it. And actually, other people I've spoken with who are not in that industry, but maybe are in other industries. So, for example, I know the head of R&D for Agilent. They make a lot of HPLCs, so column chromatography. And I talked to him. They use a lot of vacuum pumps, and I said, could you make this more energy efficient? And he said, oh yeah. And I said, well, would you be interested in doing that? And he was like, of course, if that were something that was important to our customers or became important in the market space, then yeah, of course we would do something about it. So I thought that was really interesting because I was like, well, it's pretty amazing that actually there's a lot that could be done, but people just aren't doing it because why, right? So,
yeah.
But yeah, it's a good point, and I'm really excited, I think, to engage these manufacturers once we get started. They are emailing me all the time and asking me where this project is because they're so eager to get started and actually, make a difference with their products. So it's good.
Great. Yeah, we do have a question from Logan.
Yes.
If you had to guess, what percentage of the manufacturers declined to report?
Things, my guess is it's probably off by about 50%. When it comes to the other, one of the challenge science equipment is the way that sales are reported. So having worked for life science and manufacturer, I can explain this to you pretty well. So what happens is, they're reported to, I think it's called Frost & Sullivan. They're a big consulting firm. And so every major manufacturer will report their sales for a specific category. And that makes it a little bit tricky because the categories are relatively broad because they have to encompass different types of product lines from different types of manufacturers. And they're only reporting sales numbers, so dollars, not units or pieces of equipment. So as a result, when they kind of take all of this data and merge it together, and it represents a lot of different products, and it's just sales numbers, and then they kind of back that out with the average price of the sale of a unit. That's how they're getting these data. And that's why it's kind of, even when you get the data that's been reported, it's often off by a significant factor. And that's why we're really excited to actually do this market assessment, because I think we're going to uncover quite a bit that we didn't know before. And actually, I think this will be valuable to the manufacturers because I think they'd be curious to know what their market size is as well. Because these manufacturers will actually buy that information from Frost & Sullivan and then try to gauge their place in the marketplace. But again, they're just basing it off of sales and not units sold. So, yeah, great question.
Any other questions? I think that's it. I want to thank everyone for joining us today, and especially our speaker, Allison. Allison, again, thank you so much for speaking with us. And if you need to contact...
Thanks so much for having me.
Yeah, and if you need to contact Allison, please take down our contact information. You may contact me by going to our website, wcec.ucdavis.edu. If you have any questions for me, or if you would like to request an immediate copy of this presentation to hand to your coworkers, let me know or let Allison know. Thank you, everyone, for being with us today, and I hope you have a great rest of your day.
Bye, thank you.